Hello everyone, here's another IB video. Simple harmonic motions and the energies within that system. So this is topic 9.1 still, that's higher level. And we're going to have a bit of fun here with some energy derivations. The goal of this video, much like the other ones, has been to just try and explain some of these formulas on your data sheet. We've pretty much worked our way through all of them if you've been following along in this series. The last two on the list here are these two energy formulas, so we're going to try and hit those up. So I want us to think, and we could do this with a spring system or a pendulum, it doesn't really matter. Let's just go with a pendulum system. So let's think about a pendulum. We've done this before. We think about the pendulum being lifted back up past its equilibrium position. Obviously we're being careful to keep this angle less than 10 degrees so that we do not violate the small angle approximation. And so we hold this pendulum in position. Okay, so if we think about the energies, we're holding this pendulum in position. The pendulum is now slightly above its starting point, its initial frame of reference. So if I was to represent that on here, if I was to just do a nice line from here across here, this might represent the change in the height, and maybe it came from a resting height of perhaps here. Okay, so there's a difference. We've raised it a certain height, and we've been calling this x. This would be the maximum displacement that we raised this this system. Okay, so we can talk about the pendulum moving back and forth with regards to a change in the displacement. We could also talk about this in its simple harmonic motion. Once it gets going and there's no friction, it will keep going forever. We can also talk about this in terms of time. So at a certain moment in time, it may be at different points in its pendulum swing. So now let's think about this qualitatively in terms of its position. So we'll do this qualitatively first with regards to its position on this graph, and then we'll talk about it with regards to its time. But it's important to be able to visualize and think about where the system is at certain times, because these equations allow us to calculate various energy values and various different variables within those equations at differing points in the motion. So thinking back to our little diagram, we raise a pendulum up to its highest position, less than 10 degrees, and that would be, when we're holding it at rest, that was going to be the highest the pendulum will go, and therefore it's going to have its maximum potential energy. So this red line here represents the potential energy, and so if I lift the pendulum up all the way to the left, it's going to have this negative. If we say left is negative, it's got this negative displacement. As I release the pendulum, it's going to come down to its equilibrium position, which we would say is a zero displacement, and then it goes all the way back up the other side to a positive displacement. So we can talk about displacements as up, down, left or right, whatever we want. Whatever you do, it doesn't matter, because remember from our initial statements, our initial setup of the simple harmonic motion, the pendulum swing and the spring system is all represented with circular motion. So it actually doesn't matter which vectors you use, as long as you keep track of them, you can derive all of the equations in the same way. Anyway, so this is representing our motion, our displacement, and hopefully you can see this is going to be the maximum at the equilibrium position. So it's zero displacement, it's got zero potential energy, and then comes back up again. Of course, mirroring that is the kinetic energy. Obviously, when I'm holding the pendulum stationary and it's up in its highest position, it's got zero kinetic energy, and in fact when I let it go, the kinetic energy gradually increases. It's got its maximum speed at the equilibrium position, and then it comes all the way up to the other side again, and even though I'm not touching it, it's going to momentarily stop while it changes direction, and then it comes back again the other way. Okay, nice and straightforward. In a perfect hypothetical situation with no friction, we would also conserve our total energy. So the total energy of the system will be conserved over time, and we can represent that with a green line. Okay, good. How does this differ for time? Well, not that much. Let's take a look. So if we think about this as a function of time, we've got this energy again on the y-axis, and once again, same situation. I'm going to hold that pendulum on the left side. It's going to have its maximum potential energy at 0 time. When I let the pendulum go, the potential energy drops down to 0 at the equilibrium point, and then comes back up again. And this will keep going up and down forever in a perfect system. And our blue line is the kinetic energy. Obviously, it has 0 kinetic energy at the beginning. As it reaches its equilibrium position, it's got its maximum, and so on and so on. And we've got that total energy at the top. So you can see that the qualitative ideas for time and distances, or displacements I should say, are pretty much the same thing. All we're going to do, with a bit of fun and games, we're going to look at some different formulas that we've already talked about. I'll bring out the data sheet again, and we're just going to mix them together and see what we can do. There's going to be some algebra, and then at the end of this we'll have a couple of reasonably difficult example questions to go through as well. Okay, so let's have a look at our energy of a simple harmonic system with regards to displacement. So we've got this little graph here we've talked about already. We've got our displacements either side. What I'm going to do is I'm going to use what I know about motion, which is that it's half mv squared. I'm going to use this, and I'm going to combine it with a velocity equation, but the velocity equation is going to be to do with displacement, right? So remember, I'm interested in these displacement things. So which velocity equation to use? Well, I've got one here, which I can interchange sine and cosine with. I know that from our previous videos. But notice that this has a function of time. So I'm going to try and avoid that one. I'm going to use the velocity equation here. It's called actually the velocity equation. I'm using this one because its only function is to do with displacements. So I've got my maximum displacement and a variable displacement. So this means that if I know something about my system at any given point along its motion, in its simple harmonic motion, I can start making some determined values. So let's combine these two. Let's see what we do. Let's put them together. So we'll make a statement. We'll say that the kinetic energy of a simple harmonic system is going to be 1/2, of course, m, and then I'm just going to substitute that in. So it's going to be omega squared, and then maximum displacement squared minus whatever displacement squared. Well, we can simplify that because, let's think about it for a second, when the EK is at its max, so let's write a statement for EK max. So when we're talking about the maximum EK, the maximum velocity, let's come over to this graph. Where's our maximum velocity? Well, it's going to be at this 0 displacement point. So in other words, the x value is going to be 0. So we can just assume that that's a 0, which makes our EK max formula just a little bit easier. 1/2 m omega squared maximum displacement squared. In fact, we can go a step further and say that actually the total energy when the position is at 0, okay, so when there's 0 potential energy is 0, so that would be at this equilibrium position. The total energy is also going to be equal to the statement that we just said, 1/2 m omega squared x naught squared. Okay, they are the same thing, and that's clear from our diagram, right? At the equilibrium position, the blue value is the same as the green value. Obviously, if I did a better drawing, it would be more precise, but you get the idea. And already you'll notice that we've achieved one of our goals by defining the total energy of the system. Now be careful, because this, of course, is with some circumstances. There's some assumptions about this, right? So you have to know where these come from. let's play with this a little bit more just to have some fun. Let's go ahead and do our statements about energy. So we'll say the sum of the energy initial has to be equal to the sum of the energy final. We've done this before. And of course, let's say that we have a total energy initial, and it's going to be equal then to our kinetic plus our potential. So we've already made some statements about the total and the EK. Let's see if we can make a statement about the potential. So let's go ahead and say that our potential energy is equal to our total energy minus our kinetic energy. And since we have equations for these, we've already worked out both of these equations. Let's just plug them in and see where we end up. So potential energy is going to be the total energy, which is 1/2 m omega squared x naught squared, minus, so that's part of our system, and then minus our kinetic energy, which is 1/2 m omega squared x naught squared minus x squared, oops, not x naught, just x squared. And this simplifies down in kind of a fun way. Let's just go ahead and do it all. We'll just write this out as 1/2 m omega square x naught square, and then this is we'll factor this out. We'll say we got 1/2 m omega square multiplied by the x naught squared minus 1/2 m omega squared multiplied by just the x squared. Okay, quite a bit going on. Now, to make it really easy, hopefully you can see that this statement in this bracket is the same as this statement in this bracket. So just to make it really clear, if you're having difficulties here with the algebra, let's just write it in a different way, a nice and simple way. Let's go ahead and say that A minus, and then we'll put it in brackets, A minus B. Because I think that's an equivalent statement, just to simplify it down. And then to have a bit more fun, let's just go ahead and say that we'll say that A has a value of 5 and B has a value of 2. So what does that equal? Well, plug that into your calculator and you're going to get a value of 2. Well, 2 was the B term, right? So what we're saying here is this entire statement is equal to the B term. And what's the B term? Well, right there. So let's write that out. We're going to say the potential energy is equal to the B term, which is just this last bit of our complicated looking equation. It's equal to 1/2 m omega square x square. Okay, so that was fun, but just to add a little bit more fun, let's just take this a step further. I just brought this graph back down again. We saw this previously. Of course, the green line represents the total energy. So we're going to write a quick expression for the total energy as well. So we've already stated it up here. We've already got this expression right here. And we can now look at this graph and say, well, total energy must come up to this line. And so what we can do is, let's just say that, let's say that the kinetic energy is 0. So we're going to be at this point here. Kinetic energy is 0 is going to be here. Kinetic energy is 0, so the entire thing is going to be potential energy. Well, that's kind of neat, because when the entire energy is potential energy, this must be equal to potential energy being 1/2 k x naught square, x naught being the maximum displacement. Okay, that all makes sense. Well, watch this. This is kind of cool. If we remember that omega square is equal to k over m. That's a nice little thing to remember. Well, let's plug that in. We'll say that the total energy here is going to be 1/2. Actually, we'll change this just to potential energy with the condition. So let's put it underneath at x naught. Okay, so that's referring to this idea here at x naught, when maximum displacement, kinetic energy is 0, it's at rest, it's just about to turn around. The total energy, or the potential energy, is going to be equal to this equation that we've just stated. But we're going to substitute omega squared for k over m. So let's put that in instead of the omega square, and then it's going to be x naught square, because that's the statement that we've made at x naught. Okay, look at this, the m's cancel out, and you're left with, okay, so total energy at this point in time, as we predicted, is 1/2 k x naught squared. Isn't that fun? You can just play around with these, and again, I think the key is, obviously there's algebra, but the key is keeping track of these diagrams. I would definitely have a little qualitative graph in front of you representing where the energies are at different times. All right, so we'd previously talked about getting this kinetic energy formula by looking at energy in a simple harmonic motion system with regards to this displacement. Now we're going to take a look at the energy in a simple harmonic system with regards to time. So remember, we looked at this graph before. We've got this changing kinetic and potential energy as a function of time, and the idea here being that we're going to get to a statement about the total energy. Once again, we're going to get the same sort of thing. It's just an interesting qualitative to quantitative example of how we can use this idea of time. We're going to end up using the velocity equation with regards to time up here. So notice that there's this t factor in both of these. We're going to use that, and we're going to use kinetic energy, and we're going to derive it. All right, so I've picked one of these, remembering that these are completely interchangeable, arbitrarily picking cosine or the sine function. Depends where you want to start it. You're going to get the same results either way. So of course what we're going to do is we're going to insert the velocity equation with respect to time into this kinetic energy equation. So kinetic energy is 1/2 mv squared. So I'm going to get 1/2, and I'm simply going to insert this. So x naught cosine omega t. And I've just noticed that I missed out an omega. So there should be an omega in here, and then there should be an omega in here. Sorry about that. Not forgetting the square. So of course now I can just factor this out. So I'm going to get 1/2 m x naught square omega square, and then cosine square omega t. Now, this is really cool because we've seen this already. In the back of our pockets, we're going to keep this this idea that 1 is equal to cosine square plus sine square. I heard a prof once tell a joke about this with regards to a pickup line. They said a guy walks up to a girl in the bar and says, "Hey, I wish you were cosine squared plus sine squared, then we can be one." Okay, so there you go, lame pickup line joke to remember this, but it's going to play a little role in our algebra here. The other thing that plays a role here is the idea that, remember this simple harmonic motion coming from circular motion. If we have an angle of 0 degrees, and I'm just arbitrarily saying that this 0 degrees is going to be horizontal along, I can say that cosine 0 is going to be 1. So let's just keep these two statements in our minds as we make some statements here. So when cosine theta is equal to 1, that's going to be the max or the min of our graphs. Let's go ahead and say, just again, we're arbitrarily picking a cosine function here. But since we've made this statement, we're going to say that the cosine, when cosine is 0, when cosine of the angle 0 is 1, that's referring to this maximum kinetic energy right here, which of course means the potential energy is going to be 0. So we can play around with this idea of a total energy statement once again, and in this case, we're going to say that the total energy is the kinetic energy. And since cosine is 1, we can essentially ignore the cosine function in here. So this simplifies down, and we can now say that the total energy under this condition is equal to the kinetic energy, which is then going to be 1/2. So I'm going to use this statement here. I'm going to say it's 1/2 m x squared omega squared, and that's an x naught. So here's where we get to have a bit of fun again. We'll do our conservation of energy statement. Energy initial is energy final for any given system. So let's go ahead and say that we have a total energy that's going to be equal to the kinetic energy, the EK. Let's do that again, that's terrible. The EK plus the potential. Okay, so what's the potential? Well, the potential is going to be, of course, the total minus the kinetic. And we know these, we've just made some statements about them. So the total, as we just mentioned, is 1/2 m x naught squared omega squared minus, now the kinetic we had previously made a statement about up here. And hopefully you can see this is where the cosine squared idea is going to come in as we simplify this down. So the kinetic energy is 1/2 mx naught squared omega squared cosine squared of omega t. So finally, just to simplify this down a bit, this is where we get to use our cosine squared plus sine squared. If you can recognize that this function here is the same as this function right here, we're basically saying that this, let's just call this a minus a cosine squared function of omega t. And we know that 1 is equal to cosine squared sine squared. So we can also say, we can write this out as a cosine squared must be equal to 1 minus sine squared. And so it's sort of like the same thing here. Let's just write this out again. We're basically saying that a minus a cosine squared omega t is equal to a sine squared omega t. And so we can do a straight swap. We can switch this whole function out here for a sine function. So, sorry, this whole function, so that a minus this bit is equal to just this bit. So to simplify it, let's go back to blue. We're just going to say now that the potential energy, which we were talking about all along, is equal to 1/2 mx naught squared omega squared sine squared omega t. So that's what we kind of end up with, just to simplify it down. Just a bit of fun, lots of playing around with these algebra. Again, really important to remember that we can use these ideas throughout just to simplify things down. And once again, reiterating the importance of thinking about the systems qualitatively so that we're able to define the assumptions that we're talking about. All right, so let's have a look at some example questions. Here's one for you. We're given a graph. This is the potential energy of a system as a function of the displacement squared, and that gives us a nice linear line. We're told the mass of the object in simple harmonic motion is 40 grams, and then we need to calculate the period and the maximum speed. So let's just think about the graph for a second. Looks like this is the maximum potential energy. So this is the maximum potential energy, which means this value down here is going to be the maximum displacement squared. So that's kind of going on here. And then as the displacement decreases, obviously the energy decreases, and this thing is going back and forth, back and forth, back and forth. So just, it's worth mentioning this 80, this is the EP max, and then this down here, this is going to be the x naught squared max. Oh, actually I don't even need to put max, because we know that x naught is the maximum displacement. Okay, so here's our data sheet. What might we be able to use? Well, we know that the EK of a simple harmonic system with regards to displacement is this equation here, and then the total energy of a system, whether or not it's with regards to time or displacement, can be stated with this one. Well, since this is going up, back and forth, I think we're going to go with total energy. So we're going to go with, we'll be using this total energy equation. The total energy of the system is 1/2 m omega square x naught square. So we could solve this by plugging some numbers in. Since we know the maximum, the EP max, of course, EK is going to be 0, so the EP max would be the total energy. So we could go ahead and plug 80 in here, and we could put the 4 in here. And then we also know that, let's just write this to the side, we know that omega is 2 pi over period. So once we plug the numbers in, we could get a value there. But I think it'd be more fun to do a little bit of calculus. Of course, to do that, we need to get the slope. So however you do that, you're going to do rise over run. Pick any points that make sense on the graph. And if you do that, you're going to get a slope, I think, in this case, of 2. And the units for that are going to be mj's over, actually, back it up, I think I accounted for the millijoules. So just joules over displacement squared. So, of course, the units are going to be meters squared. Either way, you get a slope of 2. And then we're going to just map out our y is equal to mx onto our equation of interest. And you'll notice that the y corresponds to the energy, and the x-axis here corresponds to x squared. So that's all good. So in other words, what we're saying is that the slope, the m, is equal to this part of the equation. So the slope is equal to 1/2 m omega square. And we know what the value of the slope is. The slope value is equal to 2. So 2 is equal to 1/2 m omega square. Now remember that omega square is 2 pi over t. So we can go 4 pi squared over t squared. And if we keep going with this, we're going to end up solving for period. So the period is equal to 1/2 m 4 pi squared over 2, all square rooted. And that should give you a value of 0.0628 something something. That's going to be in seconds. Let's just check our significant digits. We had 2 in the question, so I'm going to go to 2 in my answer. So the period is going to be 6.3 times 10 to the -2 seconds. Alright, so next up is calculating the Vmax, the maximum speed. And I just want to remind us of this qualitative graph of displacements into velocities. So we've seen this many times before. If I start my measurement at a 0 at an equilibrium point. It's going to go up to its maximum displacement and back down again. Of course, if I then looked at the velocities on this graph, so if I plotted velocity max, and let's just do that, negative velocity max, at the equilibrium point, that's when it's going to have its maximum velocity. So at the equilibrium point, the velocity actually starts way up here, and then by the time it gets to its maximum displacement, it's going to have 0 velocity. So this is going to come down to here. And then we keep going. At this point here, it's going to have its maximum negative slope. So way down here. And then once again at this point, it's going to be 0 and so on. Just wanted to remind us of that so that we can say that, once again, we're going to make this like qualitative statement. The total energy at the VK max is going to be equal to the kinetic energy. That's it, because there's going to be 0 potential energy. In other words, the maximum, well, let's pick this one here. This maximum speed should be equal to the 0 displacement. In other words, maximum speed, 0 displacement. So we can go ahead now and say that our total energy is equal to this 1/2 mx0 omega square. Actually, that's, sorry, x0 square omega square. But this is equal to our EK as well. So I can rewrite this as 1/2 mx0 squared omega squared. Now this is just equal to straight up kinetic energy. So 1/2 mv squared. And there's the v that we need. We need that v. Things cancel out. So I get rid of my half. I get rid of my mass. And I'm left with v squared is equal to x0 squared omega squared. So of course I just have this v x0 omega. And omega is 2 pi over period. So now I just have to find out what x0 is. Well, 2 ways to do that. I could just read it straight from the graph. So I have my x0 squared. We just have to be very careful when we're dealing with squaring something and converting it. So let me just show you what I mean. Basically, what have we got? We're going to have the square root of 4 centimeters squared. That's going to give you 2 centimeters. We have to be careful here, and all I'll say at this point is do not convert this to meters at this point. If you convert this to meters, you're going to end up getting a square function or a square root function of a conversion, and that's what we want to avoid. So just go with the centimeters for now. We'll convert it later as we need to. The other way you could do this would be just to use our equation. So you could take the total energy equation. You could say ET, because you know what the total energy is. It's 80, and then you got 1/2 m omega squared x0. So we could take, well, that's going to be squared. We could take this, since we know, and we would have to just put that in. So we'd have to say 2 pi over t x0. This is all going to be squared. Lots of squaring going on. And of course you could just rearrange that and solve for x0. If you do that, you plug that all into your calculator using the 80 millijoules that we were given in the question, you'll get 2 centimeters. So either way it works, doesn't matter. Just make sure you plug in that 2 centimeters, convert it to meters, and then you're going to plug it into this equation. And we know the period, so we're going to just have to plug this guy in. Obviously we won't be rounding it to 2 sig digs at this point. We'll keep the full value in our calculator to do the final calculation. So we end up getting 1.99 something something meters per second, or meters second, like this. And we're going to round this up once again. We need to go to 2 sig digs. So my maximum velocity is 2.0 meters per second, or actually in IB language, meter per second. There we go. Okay, so we're going to do one more example. We previously did an example where we used the slope of a line. This time we have our familiar simple harmonic motion situation. So we have a graph showing the simple harmonic motion given in kinetic energy on the y-axis with a time along the bottom. And so we can hopefully, knowing the mass of this object moving back and forth in simple harmonic motion, we should be able to get the period, the maximum displacement, and then the kinetic energy at a given displacement. Now, the reason I wanted to show you this is because this could be perceived as a bit of a trick, and I just wanted to draw our attention to it. What is the period of the simple harmonic motion? Okay, so warning, this is not the period of the wave, okay, or not the period of the graph. The period of the graph, would be going from peak to peak or trough to trough or whatever. If we look at the period of this graph, if we start down here and come to here, we're going to get to about here. So we would say the period of this graph is about 0.18 or something like that. But think about what's happening with this object, let's call it a particle with a mass, or a thing with a mass, and it's undergoing simple harmonic motion. Let's go ahead and just visualize that for a second. Here's my little object bouncing back and forth, whether it's attached by springs or whatever, it doesn't matter. It is undergoing simple harmonic motion, could be a pendulum, could be a spring. Let's visualize this going back and forth. Okay, the kinetic energy, let's start this at 0. So we're going to start with kinetic energy being 0 at 0 time point. That means that this object has to start at one of the maximum displacements, so at either end. Let's start it on the left. So at this point it has 0 kinetic energy, and we're going to ask the question, what happens to it as it moves through, and what is its period? So here it is, 0 kinetic energy. It's going to move here and back, here and back. So at the beginning, at 0 seconds, it has this 0 kinetic energy. The next time it has 0 kinetic energy is over on this side. Okay, so it's gone through this whole motion. It's got its maximum kinetic energy at the equilibrium point, which is right in the middle. Okay, so maximum kinetic energy would be as it moves through that middle piece. And then at this side, it's now at 0 kinetic energy again. So this is the point where it's at the other side. So be very careful. That is not yet a period of the simple harmonic motion, is it? It has to move all the way back again. So it has to come back past the equilibrium position, meaning that it's coming back through its maximum kinetic energy and returning to its original position. So the original position is going to be the third time with which it experiences 0 kinetic energy. So it starts here, maximum kinetic energy at the equilibrium point, reaches the right-hand side of our diagram with 0 kinetic energy, comes back through the equilibrium position again, and returns to its original position. So this is very important. It's very easy to make this mistake. Okay, this is the point where I'm interested in the period of the simple harmonic motion. Okay, not the period of the sine graph. Okay, and that's key. So let's go ahead and write that in. We've got all the information we need now that we've visualized this. I can go ahead and say that reading the graph, I'm going to say that the period is 0.35 seconds. It's about halfway between the 3 and the 4. Alright, so part B, we want to know the maximum displacement, and I actually forgot to include some information previously, so I've added it in. It's this maximum energy. So the maximum kinetic energy when it's going through the equilibrium position is 0.8 joules. So we can say a couple of things about that in order to get our maximum displacement. I'm going to go ahead and say that the total energy is going to be 0.8 joules. Okay, that's the maximum energy available, and that's equal to the EK max. So I'm going to look at my data sheet, and I've got a couple of formulas to use. Remember that this formula here we derived from considering the energy with regards to a displacement. This one we derived with energy regards to time, and hopefully you can see that this got this total energy which is going to match here, and conveniently we also have the maximum displacement, which is what we're trying to get. We know the mass, that's a given, and the omega, the angular frequency. Well, we know something about the angular frequency. We know that, let's write that down as well. Oh, it's already on here, pardon me. It's right here. The angular frequency is 2 pi over t. And so we know the period. We just worked that out. So we're going to be using this value. We're going to be using this value. We're going to be using this value. And that should solve for x naught, which is the maximum displacement. So let's go ahead and just write that out. So I've just said that 0.8 is equal to this equation, and now I can just go ahead and rearrange it all. So I'm going to go 2 times 0.8 over the mass, which is 0.25, and that's equal to, here's where I'm going to introduce this guy. So it's going to be 2 squared, which is 4, times pi squared over t squared, and then I still have my x naught squared, and so my x naught on its own is going to be t squared to 0.8 over, actually let me put the t in, let's go back, so it's actually going to be 0.35, there's my period, and that's going to be squared, and then 2 times the total energy, 0.8 joules, and that's all divided by 4 pi squared times the mass, and then the whole thing square rooted, which gives you 0.14 meters. Okay, part C, we need to know the energy, the kinetic energy at a certain displacement. So again, we're looking at our formula sheet, and hopefully we can recall, that this guy here, this guy is going to give us our differentiate with our displacements. So I already know, I know the period, so I can access my omega. I know the maximum displacement, and so really what I'm doing here is I'm just plugging everything in. I also know the displacement at which I'm interested. So this is just a case of plugging things in and getting the right answer. The key here is just recognizing that it's this guy with a little bit of this guy. So let's go ahead and plug it all in. So here we have it. We've got 1/2 the mass, and then our omega squared, which we've substituted in for 2 pi over t squared, and then the x naught, which is the maximum displacement squared, minus the displacement that we're interested in squared. So this is going to tell us the kinetic energy of this object as it's bouncing around back and forth, and if the maximum displacement is 0.14, the maximum displacement is 0.14, so this ball moving back and forth, the maximum displacement would be from the end to the equilibrium. We would be interested in the EK at a certain distance from that equilibrium. And so when we plug this in, we get a total of 0.53 joules. And just checking our significant digits. Well, the only value we are given is 0.25, so that's 2 significant digits. So we're okay here. We've done 2 significant digits in here, and we've taken 0.35. Well, that's an estimate from our graph. So depending on how many grid lines you have on your graph, you can kind of arbitrarily pick a significant digit on that one. But there we have it. A couple of detailed examples for us. Hopefully that helps, and we'll see you next time.